Alright, welcome back everybody. This is our second video for section 9.1 of AP Calculus BC, defining and differentiating parametric equations. In this function in this video we're going to focus on differentiating parametric functions and how we can use the derivatives of parametric functions to answer some questions about those functions. Alright, so since we have parametric functions, x is a function of t and y is a function of t, the derivative that we're concerned with when we're talking about parametric equations is we're concerned with the derivative dy dx, because the graphs of these parametric functions, and if you remember from the last video, it looks exactly, pretty much like a rectangular curve, and the derivative at any point in time is going to be the change in y with respect to x. So that's the derivative that we want to find. In order to find dy dx, we can do that pretty easily. If we take the derivative of the function y equals g of t, that gives us dy dt. And if we take the derivative of the function x equals f of t, that gives us dx dt. And then from the chain rule, you should remember that dy dx is equal to dy dt over dx dt. So all we're going to do in order to get the derivative dy dx for a parametric function is we're going to take the derivative of the y equation and divide it by the derivative of the x equation. And that will give us dy dx in terms of t. Okay, it says here a curve is differentiable if it's differentiable at every parameter value. And the curve is smooth if both f prime and g prime are continuous and are not simultaneously zero. When they are simultaneously zero, we're going to have some kind of cusp point or a corner in our graph that's going to occur. Okay, something else that you need to be aware of, we didn't really talk about it a whole lot, and I'm not going to talk about it a whole lot, is that the domain of this parametric curve is the intersection of the domains of the two equations. So for instance, when we get to example 3 and find dy dx, the domain of this curve is that, t can't be equal to 0. And the domain of this curve is that t has to be greater than 0, since the natural log has to have an argument greater than 0. And so the domain of this entire function is the intersection of these two individual domains for the parametric equations. And so the domain of this particular parametric curve is t greater than 0, since that's the intersection of these two domains. All right, let's go ahead and we'll start finding derivatives. And you'll see that this is not a terribly difficult process. So if we want to find dy dx for this parametric curve, I'm going to start by finding dx dt, taking the derivative of 1 over t, and the derivative of that is going to be negative 1 over t squared. And then I'm going to find dy dt, and the derivative of dy dt, the derivative of negative 2 is 0, and the derivative of natural log of t is 1 over t. And so now dy dx is going to be equal to dy dt divided by dx dt. And then all I want to do is simplify this equation to get my derivative. Remember this, I can just go ahead and multiply by the reciprocal. And we end up with dy dx being equal to negative t. And so that's our derivative, dy dx in terms of t. Example 4. Find the value of dy dx when t equals 2 if x equals t squared plus t and y equals t squared minus t. Again, same process. We're going to find dx dt. That's going to be 2t plus 1. I'm going to find dy dt. It's going to be 2t minus 1. And so dy dx is equal to dy dt over dx dt. And so dy dx, when t is equal to 2, we're going to just go ahead and evaluate that at t equals 2. Substitute 2 in there for t. And we end up with 3/5 as the value of dy dx when t equals 2. All right. Example 5. Find the equation of the tangent line to the curve defined by x equals t squared minus 3t and y equals t cubed at t equals 1. Equation of the tangent line. If you remember from our previous discussions, whenever we're finding the equation of a tangent line, we need two things. We need a point and the slope. So first we're going to use these parametric curves to determine the value of the point. So I'm going to find x at time 1. That's going to be 1 squared minus 3 times 1. That's negative 2. And y coordinate at 1 is going to be 1 cubed. That's 1. And so the point of tangency for this curve is negative 2 comma 1. And then I need the derivative at time 1. So I'm going to go ahead and find dx dt. That's 2t minus 3. I'm going to go ahead and find dy dt. It's going to be 3t squared. So dy dx is equal to 3t squared over 2t minus 3. So dy dx at t equals 1 is 3 times 1 squared minus 2 times 1 minus 3. And so my derivative is negative 3. And now I have all the components I need to write my tangent line. Y minus the y coordinate is equal to the slope times x minus the x coordinate. And there's my equation of my tangent line in example 5. All right. One more example. Consider the parametric equations x equals 2 plus cosine of t and y equals negative 1 plus sine of t for time 0 to 2 pi. Find the t values where there are horizontal and vertical tangent lines to the curve, and the equations of any horizontal or vertical tangent lines to the curve. So first of all, a horizontal tangent line looks like this, and a vertical tangent line looks like this. So, in order for there to be a horizontal tangent line, what we have is we have something that's moving from side to side, but not moving up and down. And so what happens when we have a horizontal tangent line is that every point on this horizontal tangent line has in common the idea that the change in y is 0. The y values on that curve don't change. And so to find the horizontal tangent lines, we're going to look for where dy dt is equal to 0. For a vertical line, same idea. We're moving up and down, but we don't move at all side to side. And so the change in x has to be equal to 0 when we have a vertical tangent line. And so those are the things that we're going to look for in order to find these tangent lines. Now, what happens if they're both 0? We mentioned earlier that that is indicative of a non-smooth point on the curve, but to decide whether there's a vertical or a horizontal tangent line there, we're going to actually have to investigate more. That makes this a little challenging, and we're not going to do this in this particular example. So let's go ahead and we'll find these horizontal and vertical tangent lines. Let's start with the horizontal tangent lines. So I'm going to set dy dt equal to 0. dy dt is equal to cosine of t. So we'll set cosine of t equal to 0. And then we determine the values of t, where that's true. That happens at t equals pi over 2 and 3 pi over 2. Those are the values in the interval from 0 to 2 pi, where this equation is true. All right, and we're going to do the same kind of basis. I'm going to kind of run these in parallel. For the vertical tangent lines, we're looking for where dx dt is equal to 0. So we take the derivative of this, set that equal to 0, and that's equal to 0 at time 0, pi, and 2 pi. Okay. Now, the other thing that we want to do, we've now accomplished the first task here. We've found the t values where there are horizontal and vertical tangent lines to the curve. Now, we want the equations of those horizontal and vertical tangent lines to the curve. Well, remember, the equation for any horizontal line is going to be of the form y equals some number. And the equation for any vertical line is going to be an equation of the form x equals some number. So for the horizontal tangent lines, we're going to take these t values and we're going to substitute them into our equation for y. So we've got y equals -1 plus the sine of pi over 2. That's equal to 0. So y equals 0 is a horizontal tangent line. And we've got y equals -1 plus sine of 3 pi over 2. That's equal to -2. So we've got y equals -2 as a horizontal tangent line. For my vertical tangent lines, since I want an equation of the form x equals some number, I'm going to go ahead and substitute those into the equation for x. So I've got x equals 2 plus cosine of 0. It's going to be equal to 3. So x equals 3 is a vertical tangent line. I'm going to have x equals 2 plus cosine of pi, which is going to be equal to 1. So x equals 1 is going to be a vertical tangent line. And at 2 pi, I'm going to get a duplicate here because we're at the same point we were at before. And so the vertical tangent lines are x equals 3 and x equals 1. All right. Let's take a look at what this curve looks like and, kind of see what's going on with these tangent lines. I'm going to go ahead and type this curve into my graphing calculator to take a look at what the curve looks like. So we've got x equals 2 plus cosine of t, and y equals -1 plus sine of t. And I want to graph this from 0 to 2 pi. And I'm going to change the x and y values a little bit. I know the biggest value that I can get from either of these equations is 3. So I'm going to set up my window to go from -4 to 4 so that I can get a good view of this curve. All right. And I'll path it. All right, here we go. And there's our graph of our curve. And you should see that there's a horizontal tangent line at y equals 0. There's a horizontal tangent line at y equals -2. There's a vertical tangent line at x equals 3. There's a vertical tangent line at x equals 1. And so those are all the tangent lines based off of our parametric curves. Okay, that's going to be it for this video. Join us next time for section 2, where we will talk about the second derivatives of parametric equations. All right, see you then. Have a great rest of your day. Bye-bye now.